In this video, we are going to go over exponents, so let's begin. Let's start off with some vocabulary. So this is called 5 to the third power, and each of these terms has a little has a name. So the big 5 is called the base, and that little 3 has two different names. Sometimes it's called the exponent, or you can call it the exponent, or you can also call it the power. So this is the base, this is the exponent or power. Now this 5 times 5 times 5, those are called factors. Because factors are just numbers multiplied together. So 5 to the third is the same as 5 times 5 times 5, which also equals 125 if you multiply all that together. So what an exponent is it's repeated multiplication. Be really careful. What a lot of people do on accident is when they see 5 to the third power like this, they think, oh, that's just 15. Because they think this means 5 times 3. But that's not the case. If they wanted to write 5 times 3, they'd write 5 times 3. They wouldn't write 5 to the third power, which means something different. So just as 5 times 3 is repeated addition, 5 plus 3, 5 plus 5 plus 5, exponents is repeated multiplication. So 5 to the third is 5 times 5 times 5. So that is what an exponent is. It's like an operation. So how to read powers? There are a couple different ways to read this. Some people will say this is 8 to the second power. Or they'll say this is 8 raised to the power of 2. I'm going to get to this third term afterward. But let's do the next one. 5 in the low 3, that's called 5 to the third power. Or 5 raised to the power of 3. And finally, 3 in the little 4, that is called 5 to the fourth. 5 to the fourth power. Now, some people will just call this 5 to the fourth, or 5 to the third, or 8 to the second, just because they're saving time. So rather than saying 8 to the second power, 5 to the third power, 3 to the fourth power, they just say 3 to the fourth. And that saves them some time. What else is it called? Just like this is 5 raised to the power of 3, this would be 3 raised to the power of 4. Now, I did say I would get back to the fancy names. So 8 to the second power, 8 raised to the power of 2. Sometimes it's also called 8 square. Now, why is it called 8 square? Well, if you remember squares, if you remember how to find the area of a square, it's basically length times width, or length times height, or base times height, or length times width. Let's call it length times width. Length times width. Now imagine my length was 8 for my square. So what would the width be? Well, it's a square, right? So the width would also be 8. So if I multiply those two numbers, 8 times 8, I get the area. So 8 times 8. What's another way of writing 8 times 8? That's right, 8 times 8 is the same as 8 to the second power, which is why we call it 8 square. If we multiply those two, you get 64, and we get 64 square units. All right, so 5 to the third. What is a special name for that? You may be thinking 5 triangled. Not quite. It's 5 cubed. 5 cubed? How is it 5 cubed? Now, if you remember volume, to find the volume of something or how much stuff is inside, you multiply the length. I'm doing like a curly cursive L. The width and the height. If you multiply the length, the width, and the height, you'll get the volume. So let's say the length is 5. What would the width of this cube be? Well, it would also be 5, and the height would be 5. Why? Well, the definition of a cube is like all the sides are the same. So the length, the width, and the height are 5. So how do I find the volume of the cube? You multiply 5 times 5 times 5. What's another way of writing 5 times 5 times 5? That's right, 5 to the third power. And that equals 125. Just in case you're curious, so like That's how you find the area, the volume of a cube is you multiply a number by itself 3 times. So that's why the third power is called a cube. The second power is called a square. All right, let's go to the next section. We want to rewrite each expression using an exponent. Let's try the first one. We have 7 times 7 times 7 times 7 times 7. You're multiplying 7 5 times. That is 7 to the 5th power. 3 times 3, that is 3 to the 2nd power, or 3 square. 0.2 times 0.2 times 0.2 times 0.2. You guessed it, 0.2 to the 4th power. And finally, 2 to the 5th times 2 to the 5th times 2 to the 5th. And you may be thinking that is 2 to the 5th to the 3rd power. And you are kind of right, kind of wrong. Actually, you are completely wrong if you wrote this. When you're writing a fraction to a certain power, you have to put it inside parentheses. You may even want to write this, parentheses. You have to put it inside parentheses. Why? Well, 2 reasons. One, it may get confused as 23 over 5, which it's not. The other reason, which is the more relevant reason, is when you write it like this is actually 2 to the 3rd power divided by 5, which is different than 2 fifths times 2 fifths times 2 fifths. 2 to the 3rd to the 5th power is actually 2 times 2 times 2 over 5. So those are different things. When you put a fraction, when you are multiplying a fraction by itself 3 times, or by any number of times, you need to put it inside parentheses. So go ahead and try the next couple lines. If you did it properly, which I know you probably did, this is 4 to the 2nd power, or 4 square. This is 12 cubed, or 12 to the 3rd. This is 3.4 to the 3rd power. And you may be wondering, do I have to put decimals inside of our parentheses? No, but if you did, it wouldn't mess it up. You'd still have the same answer. It's still equivalent, so it's all good. And finally, 5 to the 7th times 5 to the 7th. That's 5 to the 7th square. And don't forget, it needs to go inside parentheses. All right, let's do the next section. Find the value of each power. That means we are going to simplify this by multiplying it out. This is just 3 times 3, which equals 9. 2 to the 5th is just 2 times 2 times 2 times 2 times 2. A couple different ways you can do this. You can do 2 times 4 and multiply that by 2, which equals 8. And this equals 16. And this equals 32. So you could just keep multiplying by 2 every time. Or some people, they like to do it this way. This is 4. And this is also 4, right? And we still have like a 2 left over. 4 times 4 is like 16. And then 16 times 2 is 32. Or you might even say like, well, 4 times 2 is 8. And 8 times 4 is 32. So a couple different ways you could find the answer. But 32 is your answer. 10 to the 3rd power. It's 10 times 10 times 10, but there's a little trick. 10 to the 3rd power, you just write 1 with 3 zeros. Easy. And guess what you do with 10 to the 6th power? Let's write 1 with 6 zeros. 1, 0, 2, 3, 4, 5, 6. So whenever you have tens, those are actually quite easy. 12 to the 1st power, it's 12 times itself once, which means it's just 12. Well, you're not timesing it by itself, but you just have the number 12 once. You're not multiplying it by anything. 14 is 1 8 times, 2, 3, 4, 5, 6, 7, 8. So 1 times itself 8 times, and you might be thinking, oh yeah, that answer is 8. Nope, it is 1, because when you multiply 1 by itself a bunch of times, it's still 1. 0.2 to the 3rd power. This is kind of an odd one. You might be thinking 2 times 2 times 2, well, that's 8, and so a decimal makes it 0.8, but that's not correct. So this is 0.2 times 0.2 times 0.2. So 0.2 times 0.2 is, well, let's work it out. That is 4, and then we've got 2 decimal places, right? 1, 2, which means we got to move our decimal 2 in. And then we have to put our little 0 right there. So that's 0.4. Now we have to multiply it by 0.2 again. So we have 0.4 sorry, 0.04 times 0.2. You do not have to line up your decimals when you multiply. You deal with the decimals afterwards. So 2 times 4 is 8. And how many decimal places do we have? We have 1, 2, and 3, which means we have our decimal 1, 2, 3. Decimal goes right there. So let's put our decimal 0, 0. So our answer is actually 0.008 for that one. Number 16, 4/5 times 4/5. Fraction multiplication, you multiply the tops. That's 16, and then you multiply the bottoms. That's 25. We cannot simplify any further, so 16 over 25. Number 17, 1/3 to the third. That's 1/3. Again, we multiply the tops. 1 times 1 times 1. That's 1. 3 times 3 times 3. You may be thinking 9, but you are incorrect if you said that. 3 times 3 is 9. 9 times 3 is 27, so it is 1 over 27. Challenge. If you see something like this, 2 to the second power over 5, that's basically 2 times 2 over 5. And what does that equal? That's 2 squared over 5. That's 4 over 5. Okay? A little tricky, but not too bad. All right, the zero product property. This states that the value of any number except 0 raised to the power of 0 is 1. So anything to the 0 power equals 1. So 2 to the 0 equals 1. 3 to the 0 equals 1. 5 to the 0 equals 1. 10 to the 0 equals 1. 5 to the 0, that equals 1. 28 to the 0, 1. 3.7 to the 0, 1. 3 over 4 to the 0, that also equals 1. 1,000,005 to the 0 power also equals 1. Now that doesn't seem to make any sense. You would think anything to the 0 power equals 0, but let's see if we can make sense of it. So 2 to the first power is 2, right? 2 to the second power is 4, and then to the third power is 8. What is the pattern from 2 to 4 to 8? Well, you multiply by 2, right? So let's look at this. 3 to the first power is 3. 3 to the second power is 9, and then that's 27, so that's 3. 10%. So the pattern is, how do you get from 3 to 9? You multiply by 3. How do you go from 9 to 27? You multiply by 3. Same with this. 5 to 25, times 5. 25 to 125, you times 5. And from here to here, you multiply by 10. From here to here, you multiply by 10 again. So you're going to apply that same pattern. If from here to here, and then from 8 to 2 to the fourth power is 16, you multiply by 2. Well, how do you get from 1 to 2? Well, you multiply by 2. So 1 times 2 is 2. Oh, how do you get from 1 to 3? You multiply by 3. How do you get from 1 to 5? You multiply by 5. How do you get from 1 to 10? You multiply by 10. So it keeps the pattern the same. If this was 0, if you had 0 times 10, that equals 0 again. So that wouldn't work. So basically you are, and if you work backwards, you'd be divided by 10. Anyways, that's how you get, anything to the 0 power equaling 1. All right, challenge. Find the missing exponent or power. 3 to the what power equals 27. The way we can figure this out is by using a factor tree. So 27 is what two numbers multiply get us 27? Well, how about 9 and 3? Well, can we break down either? Well, 3. Well, isn't that what we needed? Was 3 to something. And 9, you probably figured out, is 3 times 3. So if you multiply 3 times 3 times 3, that's 27. So you're multiplying 3 by itself 3 times. So our exponent is 3. So it should be 3 to the third. Our question mark is the 3 right there. All right, 9 equals 9 to the what power? Well, 9 to the first power equals 9. And 2 to the what power equals 64? Let's see, this is 8 times 8 equals 64. And 8 is just 4 times 2, and that's just 2 times 2. Oh, I think I know what it is. Okay, so if I multiply 2 and 2, and notice I'm only circling the bottom of the branches. I'm not circling 4 because it's in the middle. It gets broken down. Times 2, times 2, times 2. If I multiply 2 a total of 6 times, it gets to 64. So 2 to the 6th power equals 64. Another challenge. You want to circle the equivalent expressions below 2 to the 5th. Does 2 to the 5th equal 2 times 2 times 2 times 2 times? Is that like 5 times? 1, 2, 3, 4, 5. Yeah, that is. So that's correct. 2 to the 5th equals 10? No. 2 to the 5th does not equal 10. It equals, well, when you multiply 2 that many times, what is this? 4. That's 4, 8, 16, 32. Yeah, equals 32, not 10. Oh, look at that. 32 is down here. 2 to the 5th, 2 times 5? No, it does not equal 2 times 5. 2 to the 4th times 2? Well, 2 to the 4th is like 2 times 2 times 2 times 2, right? And then if you multiply it with 2 one more time, isn't that just 2 times 2 times 2 times 2 times 2? Isn't that just 2 5 times? So yeah, 2 to the 4th times 2, that is 2 to the 5th. 3 to the 3rd. 3 to the 2nd times 3, isn't that just 3 times 3? And then you're multiplying by 3 again. Isn't that 3 to the 3rd? Yes, it is. 9 to the 3rd. This one's a little bit tricky. Well, first of all, 3 to the 3rd is 3 times 3, which is 9, times 3 again, which is 27. Does 9 times 3 equal 27? Yes, it does. So this is equal. But why does that work? Well, isn't 9 the same as 3 times 3? And multiply that by 3. So yeah, it does work. 3 to the 3rd equals 33. Not true. It equals 27. Yes, it does. It equals 9. It does not. Let's look at number 29. 10 to the 4th power does not equal 104. It is 10, or sorry, it's 1 with 4 zeros. So 1 with 4 zeros, so 10,000 is correct. 100 times 100, what is that? Well, isn't this 1 with 4 zeros? It is. Or you could say, well, 100 is like just 10 square times 10 square. And 10 square times 10 square, that's 10 times 10 times 10 times 10, which is 4 tens multiplied together. That is correct. Oops, that's not C. This is C. 10 square times 10 square. Isn't that what I just said before? Yeah, that is correct. And 10 times 4, that is not correct. And the idea of exponent. So this is just kind of an idea, exponential growth. Imagine you were given 2 offers. Take $1,000 every day for a month, which is 30 days, or take a penny and double that amount each day for a month. Which deal would get you more money in the end? Do you think that amount would be pretty close? Well, let's think about it. If you take $1,000 a day for 30 days, that's like 1,000 times 30, right? You'll end up with like $30,000. What if you take a penny and double it? Now, just so you know, it's technically not 0.01 raised to the 30th power, because it's actually, a penny would be 0.1. That would be to the 0 power. So you would almost be starting at the 2nd power, and you wouldn't want to start off with 0.1. You'd actually say, you'd actually say like 2 and start with that. And there are complicated reasons for that, but let's think of it. On the first day, you have 1 penny, right? By day 2, you have, you double it, that's 2 pennies. By day 3, this is day 1. By day 2, you have 2 cents. By day 3, you're doubling it again, so 4. By day 4, you're doubling it again, and you have 8 cents. So let's take out a calculator. Let's see what we can figure out. So we've got our calculator, and we've got a penny, and we by day 2 we have 2 cents. By day 3 they hand us 4 cents. By day 4, by day 5, by day 6, by day 7, by day 8, by day 9, by day 10, by day 11, by day 12, by day 13, by day 14, by day 15. So by day 15, you're still only getting you only got $163. So you're halfway through, and that's not even $1,000 yet. By day 16, let's see what we get. By day 17, by day 18, whoa, hey, by day 19, wow, you're getting more than 1,000. By day 20, by day 21, by day 22, by day 23, you have already gotten 41,943 plus all the money from before. So yesterday, you got 20, like almost 21,000. That's day 25, right? This is day 26. Whoops. By day 26, by day 27, by day 28, by day 29, by day 30, looks like they give you on the 30th day $1,342,177.28 plus all the money from the previous days. So that's a lot of money. It's way more than 30,000. So exponential growth is kind of crazy. If you're the kind of person who's like, oh yeah, totally, I would totally take $1,000 every day. It looked pretty good by even by day 15, you're like, I'm only getting a couple $100 halfway through. But once you start growing like 100 and 1,000, it gets humongous. So, by the way, like I said before, that the way you write the math for that is not 0.1 to the 30th power because for a number of complicated reasons. But we just wanted to kind of illustrate what exponential growth is. Exponential growth is kind of insane how big things get, how quickly. So anyhow, that is it for exponents. Hopefully you understand the concept. Go ahead and try some problems on your own. Good luck.